Hi guys, Mr. Rocco here. As you're aware, we are fully remote this week, as I will be posting, as I always do, my videos all on Canvas, which will take you to YouTube. Again, please subscribe if you haven't subscribed to my channel. There will be a few assignments this week, and there will be a new lab. If you did not do the Ellipse lab, then please make sure you get that lab done as soon as possible. The new lab, I will try to work on some of it with you during Zoom this week. So when you have your normal schedule, whether you're purple or gold, and you are an in-person student, you will come on to Zoom. The schedule was emailed to you or to your parents. Please check that email. I will also post the schedule on my announcements, so check that schedule. And yes, you are required to come on Zoom. We're going to work on the lab on Zoom this week, and then any other questions you might have on some of this week's material. So we're still working on topic 4. Topic 4 is, we started last week with insolation, which had to do with sunlight. We also covered the greenhouse effect last week. This week it's going to be the other half of this unit, which is on energy. We'll probably need to, we'll need this week and next week to finish this unit, but I should be done with this topic 4 by the end of next week. And then I will give you some kind of assessment, test or quiz on topic 4 on Kessel Learning. So look for that to come up in another couple weeks. So let's jump right in to energy. Energy, by definition, is the ability to do work, like lifting a chair. So if you're at home and you lift a chair up off the ground, you are doing work on that chair. You are moving that mass, the chair, against the opposing force, which is gravity. So lifting a chair, lifting a box, lifting something off the ground is what they call work. Taking your energy and using it to lift it against the force of gravity. There are 2 types of energies. There's what's called kinetic energy, which is the energy in motion. So take a planet like Earth. When Earth is closer to the sun, which we are now. Last week was when we reached what was called perihelion, that term we had when we did astronomy. So we were closest to the sun. The gravitational pull between the Earth and the sun was at its strongest, and so Earth's kinetic energy was at its highest. We were moving fastest than any other time during the year. When we get further from the sun and we get out to aphelion, that's going to come up in July 4th, we will be at that point where our potential energy will increase. We will store our energy. That's like a boulder sitting on top of a hill and is about to start rolling down the hill. Right before it starts to roll down the hill, its energy is stored up in the boulder, so it's got a lot of potential energy. And then that energy gets transferred or switched to kinetic. So energy is either one or the other. It's either potential or kinetic. And I have a video here on roller coasters, which go through both types of motion, energies, kinetic and potential. So let me play this YouTube clip for you. This is kind of cool.
Imagine being strapped into a big chunk of metal, raised over 120 meters into the sky, and then dropped, whizzing over hills and even looping upside down. When you put it that way, roller coasters can seem a little terrifying, but they're also exhilarating and involve some really interesting physics to make all those speedy, gut-dropping thrills work. Most roller coasters start off with something called a lift hill, which mechanically lifts you to the top of the first and tallest hill. But other roller coasters start a little more suddenly. They're rapidly propelled forward thanks to hydraulics, the branch of physics that deals with fluids and how different mechanical forces affect them. Hydraulic launch systems work by using a cable that's attached to 2 important pieces: a catch car, which connects to the bottom of the roller coaster train, and a giant winch, which is basically a huge spool that winds the the cable when it's turned by some motors. So to launch the train, this cable pulls it down the tracks, like reeling in a fish, really fast. After a few seconds, the catch car releases the train so it can zoom up the big hill. It's kind of a complex mechanism, but we'll go over the basics. A hydraulic fluid and some nitrogen gas are separated by a piston inside this chamber called a hydraulic accumulator. And the key to these launch systems is the fact that liquids, like hydraulic fluid, are incompressible. So the hydraulic fluid is pumped into the accumulator and compresses the nitrogen gas, so there's more gas molecules bouncing around in a smaller space, which increases the pressure. Nitrogen gas is cheap, easy to get, and won't react dangerously to heat and high pressure. Basically, no huge explosions. And once the pressure is high enough, a valve is opened and the hydraulic fluid rushes out to power a bunch of motors, which turn the winch, which pulls the cable, and accelerates the train. Just like that, within a couple seconds, you're speeding along at hundreds of kilometers per hour. So now that the ride's started, you've made it to the top of the first hill, and you start to head over the other side. You might feel something weird, like besides the adrenaline or other chemicals that give you that exciting rush, there's that sinking feeling in your stomach, and you might feel weightless. That's because you're in free fall, meaning that gravity is the only force acting on your body. Normally throughout the day you're able to feel your weight because something like the ground or a chair is pushing back on your body, from your feet to your bones and organs. But when you're in free fall, you're not being supported by anything, so there isn't a force pushing upward on you. You're just accelerating toward the earth at 9.8 meters per second squared like any other falling object. Now, all good or slightly terrifying things have to come to an end, so the roller coaster train needs to stop somehow. Traditionally, roller coasters use brakes that come in contact with the speeding train, like something that skids along the bottom or clamps that close around metal fins on the cars. These brakes rely on friction, which causes the kinetic energy, the energy of motion, to be converted into heat energy and stops the train. And these brakes work, but they get worn out from all this contact. But there are some brakes that don't involve friction. They work by moving a conductor, like the metal fins sticking out from the train, through a magnetic field. A magnetic field can be produced by electric currents, like the currents running through a wire, or the microscopic currents formed by electrons moving within atoms, which is kind of how permanent magnets work. So on the tracks of some roller coasters, there are rows of permanent magnets that create a magnetic field. And when the metal fins pass through the magnetic field, it induces a ring-like current called an eddy current. This has to do with Lenz's law, which essentially tells us that conductors, like these metal fins, don't like change. So when the fins enter a magnetic field that wasn't there before, they'll create a current that makes its own magnetic field that opposes this change. The train will slow down because the kinetic energy of the moving train is dissipated as heat by the eddy currents flowing through the metal. And eventually, the train comes to a stop, all without friction. So whether you love them or hate them, hopefully knowing some of the physics behind roller coasters can make you appreciate them a little more. Thank you for watching this episode of SciShow, brought to you by our patrons on Patreon. If you want to help support the show, you can go to patreon.com/scishow, and don't forget to go to youtube.com/scishow and subscribe.
Okay. I love roller coasters. I don't know about you, but I always hit the roller coasters when I go to the parks. They're kind of cool. Okay, so energy has two properties. It has electrical properties. Oops, that's a horrible straight line. Electrical, and then magnetic. And so they come up with this big word, electromagnetic. And so you have electromagnetic energy, which I'm going to call EME, short for electromagnetic energy, is moving. So that's why it's kinetic. So it says electromagnetic energy is kinetic energy contained in a moving photon, traveling in what's called a transverse wave. So what you're looking at down here below is a transverse wave. Looks like an ocean wave going up and down and up and down and up and down. The speed of light, which again is really not correct terminology. It's the speed of all the energy coming from the sun, right? The sun doesn't just give light. It gives off gamma rays and X-rays and ultraviolet. And so all that energy traveling from the sun, including light, travels at 186,282 miles per second. And so what you're looking at here is, let's say, a light wave traveling in a transverse fashion, up, down, up, down, up, down. And what you can actually measure is what's called the frequency. Frequency is how many waves per second. I don't know if you can see down here, from right here to here is a second, from here to here is another second, and from here to here is another second. So you've got a timeline here of 3 seconds. You can see in this first second over here to the left, that is one wave. It starts right here at the middle. It goes up, that's called a crest. We'll go over that in a minute. It comes down into what's called a trough, and then back up to the midpoint again. So it goes middle, it goes up, crest, down, trough, back up, midpoint. This is one wave per second, or what's called hertz. It's spelled Hertz. They abbreviate it Hz. And so when you measure energy, you're measuring the frequency. And this would be 1 cycle or 1 hertz per second. You'll notice if I go to the middle, now you see how many waves. You see 2. It goes up, down, back to the middle, and then up again, down, back to the middle. So I shortened the wavelength, see? So I made the wavelength shorter. I increased the frequency, right? There's now 2 waves per second, or 2 hertz. Then I go to this picture. Notice it's 3. So it goes up, down, back up. There's 1 wave, there's 2 waves, and there's 3 waves. So every time I shorten the wavelength even more, I'm increasing the frequency. So the shorter the wave, the more frequent the waves. I've got 1 wave here, 2 waves here, 3 waves here. I could keep going. Every time I shorten shorten the wavelength and increase the frequency, that increases the energy. So when they measure electronic devices, cell phones, you name it, televisions, your garage door opener, all of that stuff has a certain amount of energy behind it. It's measured in waves, or what are called hertz. How many waves per second? Frequency has to do with also pitch. So you take a singer that can sing a very, very high pitch has a very high frequency. So the higher the pitch, when you're listening to, let's say, a song, the higher the frequency. The lower the pitch, the more bass it is, the lower the frequency. Humans, so you take a human being, and it depends on the level at which you're listening to music. If you're at, let's say, a rock concert, you went to a concert, and some of you have probably been to concerts, I'm sure, and the music is really, really, really loud. You're talking 130 decibels. That's like blaring music coming out of speakers. The louder the music, the bigger your range is. A human being can hear from 20 cycles per second, so that's going to be really low bass, all the way up to 20,000 cycles per second. That's going to be pretty high pitch. So the range is 20 to 20,000. Now, if you were to lower the volume, right, turn the volume down, your parents yell at you, you're listening to music too loud, turn it down. All right, if you turn it down from 130 to 0 decibels, which is very, very faint, your frequency is much smaller, the range. You can't hear down to 20 cycles per second, 700. That's still low, but not as low as obviously 20. And you can't hear the high pitch at 20,000. You can only hear up to 6,000. And that's because you're listening to faint noises, if you turn the volume down on a speaker. Then you can get into animals, and I'm not an expert, but dogs, for example, right? Dogs can hear a dog whistle. Well, those dog whistles are putting out a frequency of 50,000 hertz or 50,000 cycles. So a dog can hear, 2.5 times the frequency that we can hear, the pitch, right? And that's why those dog whistles, they hear, right? And they might start barking and going crazy in your house if you had a dog whistle and you can't hear a thing. Then you go up to something like a bat, right? A bat uses frequency to fly, and a bat can hear frequencies as high as 100,000. So a bat can hear a pitch 5 times higher than a human being. Extremely high pitches. Unfortunately, we're not in school. Well, you could do this at home. I have this hearing test. I usually do this when we're in person. I give my students a hearing test. It's for fun. And so you would click on this. And you can go, I can even put this link if you want on my announcements. I have the kids just do it for fun. It starts with a very low frequency, and then it'll go all the way up to really high pitch. I think it goes to 15 or 16,000 hertz. So it'll go from 20 hertz to 15, 16,000. I won't do that on my video, but I'll put a link if you want to give yourself a hearing test and make sure your hearing is good. These are some common frequencies. So again, the higher the frequency, the higher the hertz, the more energy it has. Something has more energy. So AM radio, AM is very low. That's why AM stations, you can't go very far and listen to an AM station. Their frequencies are 535 kilohertz to 1.7 megahertz. So kilo means 1,000, mega meaning a million, but that's a low frequency. And that's why AM stations, you don't go very far. They use them at the drive-in movies. If you go down to Hyde Park Drive-In, they'll have you turn your radio to a certain AM station. Where else are AM used? Colleges. So a lot of times your college radio stations, if you Marist or Bard College or Vassar, they will have radio stations, people that are communication majors, and they will broadcast, but they broadcast on AM because an AM station doesn't have a lot of power. They don't want college music and college information getting broadcast to all over the Hudson Valley. So they put them on a very low AM frequency. Your shortwave radios, that goes 5.9 to 26 megahertz, so those can go pretty far. A television station, anywhere in the low numbers, 2 to 6, 54 to 88 megahertz. Your FM radio, 88 to 108 megahertz. So again, like, what's the one in Poughkeepsie? K104. So that's 104.7. When you tune to that number on the radio, that's what you're tuning to. You're tuning to 104.7 megahertz. So the number on a radio is the frequency, is the hertz. In this case, megahertz, which is millions of hertz, millions of cycles per second. So I don't know if you ever knew that. So when you tune into 104.7, see, it's in that range between 88 and 108. TV stations that are higher on the channel, 7 to 13, they're going to have more power. So 174 to 220. A garage door opener, right? You don't want to be able to open your garage from another state, right? You want to be able to open your garage when you pull in the driveway, or maybe as you're coming down the street, it might work. But they're only going to have 40 megahertz, which is not a lot. A cordless phone, anywhere from 40 to 50. Again, a cordless phone, you can go so far. You might be able to walk to your mailbox and be able to use the phone, but you're not going to be able to obviously go way down the road and still be able to talk on your cordless phone. A baby monitor, again, not that much power. You don't want to be able to broadcast, the picture of what your baby's doing, sleeping in a crib to all your neighbors, so you keep it on the low end. RC control cars, 75 megahertz, you can go so far with them. A cell phone is pretty decent, 824 to 849 megahertz. Air traffic controllers, GPS system, now that's going to have a lot of power. 1227 to 1575 megahertz, right? Because those have to be able to track you all around the Earth. And then your really deep space communications, stuff that's looking at galaxies far, far away, they go up to, 2300 megahertz. Now, the other type of wave, again, transverse waves go like this, up, down, like ocean waves. These are called compressional waves or longitudinal waves. Imagine these are a bunch of springs. And what would happen here is if you come up from this side on the left side here and you push these springs like this, if you give it a push in that direction, it's going to cause this spring right here to kind of collapse, compress, and then expand, which pushes into this spring, which will compress and expand and keep the domino effect going. This will expand, this will compress, expand, etc. And this will go in the same direction. So a longitudinal wave or compressional wave is what it means. You're compressing these springs, causing the wave to travel in the same direction as you were pushing them. So you gave it a force in the same direction you want it to go. Whereas, see, a transverse wave, this wave is going this way, but the wave action is actually at a right angle. It's going up and down, right? It makes a right angle. See a 90 in here. So a transverse wave travels at a right angle to the way it's heading. It's heading this way to the right, but it's going up and down. A longitudinal wave is the action of the wave is in the same direction as the wave's going. So that's the difference between a compressional wave and a transverse wave. We're going to talk more about these two types of waves. When we get to like May, the end of the year, we get into earthquakes. And maybe you might have covered that in middle school. Earthquakes when an earthquake happens, they create what are called P waves and S waves. A P wave travels like this wave, a compressional wave. An S wave travels like this wave, the transverse wave, up and down. And so we'll talk about those later on in the course. Here's the two. So longitudinal waves are P waves. Transverse waves are ocean waves, up and down. Travel at a right angle. I have that written right up here. That's going to cause, when we get an earthquake, that causes a different motion. So like the first wave to usually hit when an earthquake happens are the longitudinal waves. P waves can travel faster. And so what will happen is, let's say this is the ground, and I'm doing this with a mouse, so just excuse me. Let's say I have the house. A longitudinal wave will cause a house to go this way. It'll kind of sway, or a building to go side to side. which, if it's a well-built building, can handle a side-to-side motion. A transverse wave, those are your S waves, they come in next. They're slower. And when they get to the house, instead of the house going side to side, now the house is going to get forced to go up and down. That's when all heck breaks loose, because a house is not going to have a nice, easy ride when the house gets forced up and down vertically. And that's when, if it's an older house, or you might lose the chimney or the roof will start to crumble. And so it's the transverse waves that cause most of the damage from earthquakes. Again, longitudinal, they're more just a building might sway side to side, but a transverse wave will cause a lot of destruction. Again, we'll talk more about that later. This is going to show you a transverse wave. So let's say you have a pond and you take a pebble or a large rock and you throw it into the pond, and then you get those ripples going away from where you dropped the rock. That's a top view. If you look at a side view, so you drop the rock in the water, you threw it in the water, and then you see the transverse wave going up and down, up and down, up and down. This animation will show you a transverse wave. Here it is right here. So you can see this transverse wave. Now there are a couple of places, I don't think I can pause this, where you can measure wavelength. I'll show you that in a minute. Notice they're showing you the wavelength is at actually the top of the wave. Before I was using the middle of the wave to the next middle. You can actually measure it from crest to crest, they're called, the peak. Or you could also measure it from the bottom, trough to trough. So any way you want to measure, there's 3 ways you can measure that. Let me get to that. Oh, so before I cover that, every object in the world gives off, again, EME stands for electromagnetic energy. Every object gives off EME, electromagnetic energy, in the form of heat, right? You give off heat. The Earth gives off heat. We talked about that when we did sunlight greenhouse effect last week. So again, this is the ground. Let's say this is the sun up here. Okay, and the sun gives us insolation. Insolation coming in is shortwave. So there's your shortwave coming in. The ground, remember I talked about this last week, has to turn that energy into heat. So the heat waves coming out of the ground are infrared. They're going to be a longer wave. So you see they stretch out. Not as powerful. The rule of thumb is the shorter the wave, the more energy it has. So the sunlight coming in is a more powerful, potent form of energy than the heat going out of the ground. And that's why the greenhouse gases can trap the heat. They can't stop the sunlight, right? Sunlight comes through the atmosphere, it's transparent. But the greenhouse gases can trap heat. Heat is a lower form of energy. But anyway, everything gives off infrared. And the rule of thumb is the hotter the object, the more energy it has to give off. That goes back to potential energy. So if you have, let's say, 2 people, and one person has really cold hands, and another person has really hot hands, and then they shake hands, the person with the hotter hands, it becomes what they call the heat source. They're going to give off more energy than the person with the cold hands. And so what happens there, if you, let's say, you shake hands with somebody, and again, let's say your hands are really hot and their hands are ice cold, you're going to give heat to the cold person's hands, the colder hands. And that's called a source to sink relationship, which we'll talk more about probably next week or later. Hotter objects have more energy. They have more potential. You have more stored up energy in those hot hands and more to give off. So a hotter object has more to give off. They'll do a Regents question where they'll have they'll give you 2 objects. Say object A and object B are sitting in a room. Object A is, 40 degrees Celsius and object B is only 20 degrees Celsius. Which object has more energy to give off? A. And then why? Because it's at a higher temperature. Something like that. Pretty easy. All right, so here's your waves right here. And you do need to know the parts of a wave. So this is a transverse wave. Let me go through different parts. The top of the wave right here, the peak, is called the crest. So the crest is the peak. The bottom of the wave right here is called the trough. I believe horses and farm animals will eat or drink out of a trough, right? They throw feed or water into a trough, and that's what they eat out of. So the bottom is called the trough, and the top's called the crest. The height of a wave, the height right here, if I measure from this middle line to the top where it crests, is called the amplitude. So amplitude is the height of a wave. Amplitude when it comes to music and car stereos. Let's say you bought a car, you got your driver's license, and then your music, your speakers aren't very loud. You can buy what's called an amplifier. So some kids will really soup up their car stereos and make them, much better than the stock radios and the stock speakers in their car. I used to love doing that as a kid. I did it to all my cars. Anyway, amplitude, you'd buy an amplifier. So an amplifier's job was to take these waves, and instead of them being this height, maybe it wasn't loud enough for you. Let me use a different color here. You would change the wave and make them higher amplitude. So now they'd go like this, much higher. The higher the amplitude, the louder the sound. So an amplifier's job was to raise the amplitude of the sound waves coming out of the speaker to make it louder volume. Then you have, you don't have to do that part up there. Whoa, sorry. You have to do this part. Then you have wavelength. And again, wavelength can be measured differently. You can go from this crest here, you go down to the trough, back to the crest again. So from crest to crest, that's a wavelength. Or you could measure trough to trough. I could start at this trough here, go up, back down. So that would also be the same wavelength. This distance and this distance would be the same. Or you could call it the midpoint. I call it the midpoint. So I could start at this midpoint here, go up one crest, down one trough, back to the same midpoint again. So that would also be a wavelength. So there's 3 ways you can measure wavelength: crest to crest, trough to trough, or midpoint to midpoint. And then there's frequency again, which we talked about with hertz. That's the number of waves per unit of time. Usually you look at time per second. How many waves in a second? And again, frequency changes pitch. So amplitude will change the volume. I'll put VOL, volume. Frequency changes the pitch. I'll put P for pitch. Higher frequency, higher pitch. Lower frequency, lower pitch. Okay. Now, in your ESRT, they list what's called, and one of the assignments this week is going to use that chart. It's on page 14, and it's called the electromagnetic, again, EME, energy spectrum. Energy, again, is broken down by wavelength, or classified, I should say, by wavelength. The shorter the wave, and this is the key that you want to remember down here, the shorter the wavelength, the more energy it has. Meaning, and I'll do my best with the mouse here, if I draw wavelengths that are like really squished like this, up and down, up and down, up and down, up and down, but they're really squished waves, short waves, this would have a very high energy, these waves. If I take a wave and do this to it, stretch it out, this would have a low energy. So shorter wave, more frequency, more energy. And so in your ESRT, and this is where you'll need for one of the assignments this week, they list the spectrum. Notice over here, decreasing wave over here. That means these are short wave. These are short. And over here, increasing wave. These are your long waves. And so, and you can even add this to your ESRT if you want. Make a little note on there. The decreasing wave, because they're short wave, they're going to be really squished like this. They're going to have high energy. So the more to the left you are on the chart, that's way over here, especially the gamma rays, the more energy it has. Way over here are the long waves. They're going to have low energy. That's going to be your radio waves. Radio waves are your AM. Those are your FM. Those are your TV. They're not harmful, right? They go through the walls of your house. They're going through your body 24/7. You don't even know they're going through you, and they're not causing any problems. Gamma rays, that's a different story. So the sun gives off everything from visible light. Now, you got to be careful with visible light. Visible light, they broke down into its colors as well. But if you take this violet, blue, green, yellow, orange, red, and then squeeze it back together, you see where it is. It's actually right in here. So they took visible light, which I put a V here for visible light, and then they broke it down into smaller parts, different colors, right? The colors of the rainbow. And so, let me clear this. Gamma rays are going to be your shortest wave. Again, coming from the sun, luckily we have an atmosphere, blocks them out. X-rays, those are going to be also harmful, right? You go get an X-ray, you got to not get too many X-rays, and you have to be careful. The technician always steps out of the room when they take an X-ray. Ultraviolet, right? UVA, UVB, harmful rays, cause skin cancers. All this is coming from the sun, very harmful. Visible light comes from the sun, but we need it, right? Plants use it. We use it for energy to turn into heat. Plants use it for photosynthesis, etc. Then they take the visible light and break it down also by shorter wave to longer wave. So when you look at the colors of the rainbow, violets and blues are short wave. They're decreasing wavelength because notice what side they're on. They're on the side of decreasing waves. Then over here, you get your reds and your oranges. They're going to be longer wave. Right? Remember when we did red shift? Red meant moving away. Big Bang Theory, we talked astronomy. So a red color is a long wave. Long waves, which means stretched out. Then, okay, clear this again. Visible light was here. Now you go to the other side of red, and you have infrared. And that's where you see colors of rainbow. You had violet, and then this, if I took violet, violet would be right here. And what's next to violet? Ultraviolet. Just like on the other side, the right side, you have red. Put the red right here. What's next to red? Infrared, which again is heat. So infrared is heat. Again, the earth gives it off. You give it off, right? Nothing dangerous about infrared. And then you have your microwaves, which again goes back to the Big Bang, right? They found all that leftover energy after the Big Bang. And then you have your really long waves, which are very low energy. Those are your, again, your AM, your FM, TV waves, radio waves. This just shows a prism. So you take white light. White light is just a combination of all the colors. So when you take your violet, your green, your blue, your yellow, your orange, your red, you put them all together, all the wavelengths blend together. That's what white light is. White light is just blended together. Black light, by the way, I know, I remember back in the 80s, my brother used to have these posters. They glow in the dark with these black lights. You'd buy a black light bulb and put it in the lamp, and then had these really cool posters you could buy, and they would glow. And what black light is, that's ultraviolet. So black light bulbs are ultraviolet. So certain posters, I probably could still get them. I'm sure you can find them online. Are these posters that if you had an ultraviolet bulb, will glow in the dark. They're really cool. Anyway. Visible light waves are the only electromagnetic waves we can see. So again, that's why it's called visible. Right? We can't see X-rays, you can't see gamma rays, etc. We see visible. We see them as colors of the rainbow. Each color has a different wavelength. Red is the longest wave. Violet is the shortest wave. When you put them all together, again, they make white light. Sunrise, sunsets. So people will always ask me, Mr. Rocco, how come, certain times of the day, the sun itself or the colors will change? Usually in the morning or evening, you get like nice pink or red sunrises, sunsets. It has to do with, again, wavelength, and actually has to do with light. And pollution, unfortunately. So it says, as the path that sunlight takes through the atmosphere increases in length, Roy G. Biv, there's your colors, encounter more and more atmospheric particles. This results in the scattering of greater and greater amounts of yellow light. So what actually happens is, when the sun is up in the middle of the day, like really high in the sky, solar noon, the sun being higher in the sky, notice here, it doesn't have as much of the atmosphere to go through, the sunlight. And so because it's going through a shorter distance, that's what puts it in the yellow, right? Roy, if you take the Roy G. Biv, the Y is really in the middle. It's not the longest, not the shortest. But when the sun is at a high spot in the sky during the middle of the day, the sun will have a more yellow look to it, or yellow light, because the sunlight is only traveling through a shorter distance of our atmosphere. When the sun is low in the sky, like sunrise or sunset, and that's why I wrote over here, the light has more distance to travel. It has to go through a lot more of our atmosphere. And so as the sunlight comes into Earth and is now coming from a low angle, sunrise or sunset, it has to stretch. And when, again, that's that whole idea behind red shift. You're shifting the colors toward the red end. And so now the waves get longer. Again, longer waves are on the red side or the orange. So when you get a nice reddish, orange, pinkish colored sunrise or sunset, a lot of that has to do with position of the sun. Up high, it's yellow. Down low, it has to go through more distance, so it's red. Another factor, which is also in here, the effect of a red sunset becomes even more pronounced if the atmosphere has a lot of unfortunately, particles of pollution. The presence of sulfur aerosols emitted as an industrial pollutant or volcanic activity can contribute to some magnificent sunsets. So actually, sometimes I've had, Mr. Rocco, did you see that sunset last night? It was really cool. Yeah, but unfortunately, it could have been caused by a lot extra pollution in the air that day or something going on. Yeah. So it's very ironic that you can get a beautiful sunset or sunrise, which can be caused by pollution. But yeah, that's the way it goes. So two factors, the pollution and then again, the longer distance will give you that red sunset or sunrise. So this just shows the same thing again. Red is on the long end. Notice the wave. See the wave going through this picture? So it's kind of stretched out over here. And then by the time you get to green, blue, purple, the violet, you notice how the wave got squished. So we got a shorter wave on this side. And then eventually ultraviolet. All right, real quick, 4 things that can happen to energy when it hits another object. So as sunlight comes into our atmosphere and then reaches the surface, and these are pretty easy, there's 4 things that can happen to it. It can reflect. That's easy. Reflect means to bounce off. There's 2 rays of light. I wouldn't worry. They usually don't ask this on the Regents, but just kind of an FYI. So the source of the energy is the sun. When the sunlight comes in, the ray hitting the ground is called the incident ray. After it hits a surface, let's say a snow, right? Snow is smooth and white. That's going to cause more reflection, a white, smooth surface. Then it comes off the surface of the snow. It's called a reflected ray. The way it works is they're equal. So let's say the sun angle for today is 27 degrees. So the sunlight comes in at a 27 degree, that's an incident ray. If it hits the surface at 27 degrees, when it bounces off, it's going to also bounce off the surface at 27 degrees. So whatever this angle is over here is equal to whatever this angle is after it reflects. But I wouldn't worry too much about that. I would worry about the reflection. You should know what reflect means, to bounce. And that's a really cool picture. I love that when you see like these beautiful skies where the water, a lake or whatever is like not moving much that day. There's not a lot of wind, and you get that beautiful like mirrored image on the lake water on the surface, and you can see like one sky on top of another. It's kind of cool. It's very calming, very peaceful. Refract. So be careful. Reflect means to bounce. Refract means to bend. And so what happens here is you have your source of light coming in. Let's say this is sunlight. And then here, this rectangle is supposed to represent a glass or even water. And so when you compare, the sunlight's coming through the air, right? Up here would be air. Air is less dense than water, or air is less dense than glass. So what happens is when the light comes from something less dense, and I wrote it down here, if you can see that. When it goes from something less dense into something more dense, the light will bend toward what's called the normal. The normal is just a straight up and down vertical line. So right here. So if you have light coming through and it's going to go through water, when it passes through the air and into the water, it's going to bend more vertical. Not going to necessarily go straight vertical, but just bend a little bit toward the normal because it's passing through something less dense into something more dense. Then, if you see down here again, it says from more to less, it bends away. So it does the opposite. So it's going to come from air. It hits the glass or hits the water. It bends toward the normal. So it bent this way, toward the left. Then after it goes through the water or through the glass, it bends back to the right and goes back away from the normal. And so you get this little zigzag. If I use a blue color, it started this way, and then it bent toward the normal, and then it bent away from the normal. And it makes a little zigzag. And that's refraction. And the easiest way to see refraction is something, well, you can do this too. There's a piece of glass, and this is shooting a laser beam through it. So the normal, let me use my straight line tool, would be right here. And so you can clearly see the away and the toward. So it went from air, which is up here, into this glass. It bent this way toward the normal. And then when it got out of the glass and went back into the air again, it bent away from the normal. So it bent toward the left and then bent toward the right, made a little refraction there, a little zigzag. I was going to say the best example is a pencil. Right? If you take a pencil and stick it in water, you're up here, your eye is your eyeball. You're looking at the pencil in the water. It looks like the pencil because it went from the air into the water, looked like it bent. When it didn't really bend, right? The pencil didn't bend. It's just because it went from air. You're looking from air into water, and so it looks like that. Here's an example right here. So the pen is sitting in the cup of water there, and it looks like the pen is actually bent, but again, it didn't really bend. It's just how you're looking at it. So that's refraction. I referred to Castaway. So if you ever saw the movie Castaway with Tom Hanks, it's middle of the movie, or when he's stranded by himself on the island and he's there for quite a while, and then he's getting hungry and he's trying to figure out, well, how am I going to get food? And he starts to do this spear fishing. If you watch that scene where he's spear fishing, in the beginning, when he first starts spear fishing, he can't get the fish. And that's all because of refraction. He's, again, standing in the water. His eyeballs are up here in the air. He's looking into the water. And so the fish is here, but again, because of the view he's taking, it looks like the fish is over here. So the apparent position of the fish, right, how it appears to Tom Hanks is offset. And so that's true if you've ever tried, I've never tried to spearfish, but let's say even a swimming pool, let's say you drop your goggles in a pool, and then but it's not a deep pool. Let's say it's a 3-foot pool, and you try to reach down through the water to grab your goggles, right? You might have to move your hand slightly and say, oops, I didn't grab them, because what you see in the water is not where it actually is, right? The appearance is different than when the actual position is, and that's all due to refraction. That all has to do with refraction. So it took Tom Hanks a little while there. He finally got the hang of it and realized, oh, the fish is not here, it's over here. He's got to aim a little bit to the left or a little bit to the right, and then he finally figured that out and started, spear fishing correctly. Scatter. So scatter is a combination. Light, especially off clouds or aerosols. We talked about aerosols last week. Dust particles, CFCs, chlorofluorocarbons, all this stuff that comes out of spray cans and things. Those up in the atmosphere cause both. They cause sunlight to bounce off of them and also bend as they go through them. So clouds will do scattering of light. I know I have a picture. Yeah, here. So if you ever look sometimes at a cloud, it'll cause sunlight to not only reflect off the cloud, but then sometimes, again, because this is air, I'll put A, and a cloud is really water vapor, water in a gas phase, so you're going to a different density. The sunlight will go through the cloud and then bend and refract. So you get both. That's what scattering of light will do. It'll bend and bounce off. And then absorb just means to take in. So absorb, right? Dark surfaces, and typically rough surfaces. Somebody always asks me, like, well, what if it's dark, but it's a smooth black surface? And then let's say you had a dark rough surface. So if you had two surfaces, both dark, but one was smooth and one was kind of rough, the rough surface is going to allow more absorption. The smooth surface will take some of the sunlight in, but because it's smooth, it's like glass. It's gonna the sunlight will kind of skip off of it a little bit. So typically it has to be a dark surface and rough in texture. That's going to be the best at absorption. Shingles on a roof, right? Your shingles, if you have black shingles, they tend to absorb because they're not only dark, but they also have a rough texture to them. If you had a roof, I suppose, that was a dark roof but smooth textured shingles, that would not absorb as much sunlight. Anyway, a good absorber, and this, I don't see this down here, a good absorber is a good radiator. Meaning, when it's sunny out, you got blacktop, let's say, and the sun comes out, the blacktop's going to get hot during the day. A blacktop is a nice dark rough surface. It's going to absorb a lot of energy. But things that absorb well also get rid of well. They become radiators. Radiation is to give off. And so blacktop will get hot, but once, let's say, the sun goes down, give it an hour or two, the blacktop after sunset will get very, very cold. And it'll give off that heat very quickly. So it'll kind of absorb the sunlight quick, but it'll also spit it back out quickly. Blacktop. So that's an important rule in the world of physics. A good absorber is also a good radiator. What takes it in will also get rid of it fast. And this just shows different examples here. So reflection off a white surface, you see the light coming in and then bounces off. Absorption, you got a black rough surface, takes it in but doesn't let go of it, keeps it. And then refraction, it goes through the glass and then bends. And I think that's it. So I'm going to put this on Canvas again. This will bring you to YouTube. Please subscribe to my channel. And then I will be making at least another 1 or 2 more videos for this week on energy. But this was video number 1. And I will talk to you guys soon.